Okay, hi everyone, welcome back. Today we're going to talk about a really interesting topic. Is how to quantize light, how to combine light and quantum mechanics, and then finally arrive at a conclusion we've been keep using and using over and over again. Is the we say that there's photon, right? And then the photon energy is h bar omega. Okay, and where does that conclusion come from? And this framework of quantization of light, okay, combining Maxwell equation with Schrodinger equation is kind of a very standard way in transition from classical to quantum. And you can apply the same technique to create phonon, and then also the same technique to create LC circuit where you will have microwave photon. Okay, and so let's get started. So first, okay, we can briefly review this. What is light? And this is fairly straightforward, right? Light is the electromagnetic wave that satisfy Maxwell equation. Okay, so what we have is, let's say here is, we're focusing on the traveling wave, which means there's no free charge. Okay, let's say 0, and then right, and so everyone is already very familiar with this. Right, so here we set the charge density to 0 and then current density to 0, which means we don't care about how the light is generated, but we care about how the light propagates or how the light interact with other things. So that's why you can leave this to 0. And we know that from previous class, we know that, okay, if you do a curl on this equation and substitute in that, you actually get a wave equation, and you solve speed of light. And this part is fairly straightforward. Okay, so now the question you might ask is, okay, what's wrong with this, right? Why do we need to quantize everything? And if you remember, okay, the any wave equation, classical wave equation, let's say at the end you will have, okay, there's right at the end you could have a wave equation probably like this when you do the curl here. And one thing you can notice here is that for this wave equation, the electrical wave in principle can be any number. So it's what we say is that it's continuous, right? It can reach all the way down to 0, and then you can slightly increase that to any number you want, right? To any number you want. So it's the nature of the classical physics is that things are continuous. Okay, things are continuous even though it's a wave. Okay, so but then this actually doesn't match with experimental discoveries. The first discovery, of course, is having light hitting a metal and then see, okay, whether there will be electron absorbing the light energy and then escape. But that's a little bit, that's the very first experiment that leads to let Albert Einstein propose the idea of photon. But there's another experiment that you guys can do, especially I imagine in Joe or Andrew's lab, is that if you have a laser, okay, if you have a laser, in laser we usually treat the laser as a classical instrument where you will have the electrical field of the laser as there's an amplitude and then there's a frequency and then there's a phase, right? And of course you can say, okay, there's propagation. Okay, and then you propagate this wave and then you send it to a detector. right? Send it to a detector, and the detector, what we will do is that it will tell you the photocurrent, right? How many photons do you have in here, or how well. So it helps you to, or you can think about it as it can count the energy, okay, that's within this laser beam. Okay, now think about one question here. Okay, if you put attenuator here, your optical attenuator to tune down the power, then from a classical point of view, what you would see is that because the current here should be proportional to the photon you have, or the energy you have, right? E or E squared depending on your the type of a detector. So let's say I equal to this. Then what you should see is that as you turn up the attenuation, right, less and less light can come here, and what you will see is that this is, let's say, attenuation. This is your current should drop like this, right, and all the way, very approaching zero, or if you turn all the way down to zero. Okay, but the fact is that this is not true. Okay, if you do experiment, this is not true, especially if you use extremely sensitive photodetector. Okay, what people see is that when the amount of energy, or the amount of energy in the laser beam becomes so small, then what will happen is that you'll start to see discrete energy wave pack. Okay, so if you look at time domain, let's say here is h bar omega, this is power. Okay, if you have a lot of power, then your signal will look like this, right? There's over versus time on the detector. You have lots of power, a continuous wave, a continuous current, and then it has some fluctuation because of the noise, right? But then when you attenuate all the way down, all the way down, almost there's no photon, almost there's no light, then what you will see in time domain is that you will see, there's one photon, and then there's no photon, and suddenly there's two photon, no photon, one photon, and probably three photon. Okay, so you will see that in a lot of moments, you actually don't see any light at all. Okay, you don't see any photon or any energy at all. And then at certain moment, you will see a quantized scale. You see a quantized energy, like this is h bar omega, this is 2 h bar omega, and then there's 3 h bar omega. Okay, so you will see really quantized energy level of the laser beam, hitting your detector, and then your detector can resolve it. And there's no way that you can use classical physics to explain this, right? Because when you look at your Maxwell equation and then your wave equation, there's simply no reason that when your amplitude becomes really small, then things start to change. There's simply no reason for that. So this is actually exactly why we start to quantum mechanics is actually useful in a lot of optics experiment, because you will see things that just doesn't fit with the classical mechanics, or with the Maxwell equation at all. Okay. Now let's see how quantum mechanics can possibly solve this problem. And to do that, we have to first understand, briefly review the basic mindset of the basic toolbox of quantum mechanics. And previously, we have said that in quantum mechanics, when we solve the nonlinear coefficient for chi2 or chi3, we say that in quantum mechanics, people treat, instead of solving like momentum, position, or electrical wave, magnetic wave, people don't solve that. People solve something called wave function. And in wave function, it could be in principle can be any variables, but just to make it very simple, a wave function depending on position and time. Okay, and then the equation governing this function, wave function, is Schrodinger equation, where you have basically what you have, okay, is energy in one form, right? Because if you're a wave, then you have e to the minus I omega t. Then you do time derivative, you get h bar omega, right? Equals to Hamiltonian, which is written, okay, you can Hamiltonian, which is actually just the energy, but then you written it in operator form. And previously we know that one operator, the momentum operator, is a derivative, okay, of this, okay, and then what will happen is that you use this function. Well, sorry, you use this equation, and it's relatively easy to convert this equation into an eigenstate or eigenfunction equation, and then you can solve certain eigenstate or eigenfunction. Let's see here. Okay, because H has the dimension of energy, so here the eigenfunction, well, eigenvalue, okay, eigenvalue of this eigenfunction must have the dimension of energy, so that's why we use En here as energy, okay, and you can convert from here to here by using separation of variables, eliminating the time term. We've done that previously in the previous class. And then here you can kind of say that, okay, because well, there's a theorem in quantum mechanics, because the Hamiltonian represent energy, so that the eigenvalue of the Hamiltonian of your operator, okay, is all the possible energy you can measure in experiment. And this way you will get is En, okay, will be h bar omega n plus 1/2. Okay, and that way, okay, it will explain why when there's a lot of photon, when there's lots of power, then you can see relatively it's a continuous wave, because okay, the n is very large here, so changing a little bit, you wouldn't notice a difference between classical and quantum. But then when the amount of energy is very small, then okay, you can tell the difference between n equals 1, n equals 0, and n equals 2, right? And so this is the basic logic of what we're going to do. Okay, we're going to write down so what we're going to do is that we're going to write down the energy for EM wave. Okay, write down the energy for EM wave, and that gives you a Hamiltonian. Okay? Hamiltonian is the energy, and then you can use a standard quantum mechanical way to solve this problem. Okay, and some of you might wonder, okay, why can we only measure, or can we only observe the eigenvalue of an operator that corresponding to a physics attribute that you can measure? For example, here the energy operator is Hamiltonian, and that's actually just an assumption in quantum mechanics. And there's many ways to justify that. I did those in my undergrad class for quantum mechanics, but here, okay, I would just assume that everyone either already know that or is smart enough to figure out that by yourself. Okay, so here I would say this is one of the assumptions in quantum mechanics, is that for an operator A, the possible or the measurable value in experiment is an, where Ka per psi equals an per psi, right? So again, it's the same thing, right? For any physics attribute, okay, you can be position or momentum, then the measurable value that in experiment is always your eigenvalue of your operator itself, okay? And just a little bit, brief review from a previous class is that one operator you guys learned from the previous class is momentum operator, which is, right, if it's momentum of the x position, then it's actually a derivative of x and divided by a constant. And this one is, we justify this by saying that, okay, a wave, traveling a wave, have EIKZ as its phase term, and then if you accept the concept, or if you accept the idea that h bar k is momentum, then what you will get is that, okay, you apply this derivative. Here, let's change it to x. You apply this derivative, and then what will show up in the front is h bar k is a momentum. So we call this a momentum operator. And later we will see something very similar that we define for the EM wave, that we have to adapt one of a number, okay, into an operator, okay. Okay, so now the key, okay, of quantized EM wave or Maxwell equation, well, not Maxwell equation, just EM wave, is to be able to write down the energy of the EM wave, the light, and then somehow figure out a way to change some variables into operator, and then you will have a differential equation that you can solve for the eigenstate, and that's your possible energy level for the photon. Okay, so to do that, we have to remind ourselves the very simple equation here is the energy of light let's write it down as h. Okay, h is the integration of electrical energy that's stored in the light, and then magnetic energy that's stored in the light, and do integration. And so if you have, so for a plane wave, okay, then you can write down what is E and then use Maxwell equation, write down what is B, and then do this integration, and you will get the energy. Okay, so it looks relatively simple, but it's actually very, it's actually much more complicated than that. So first of all, okay, if you want to get the energy of light, right, you have to do this for the entire space, right? Because there's no such thing. Well, because we didn't set any limit for where the light can exist, and then of course we know that it travels extremely fast, so it's everywhere. Okay, and for any integral, you don't want to handle minus infinity and plus infinity, and especially in this case, you know that the integration, if you use plane wave, right, then there's energy everywhere, so this integration will blow up, and it actually makes no sense, okay, to calculate this. So in order to simplify, okay, our mathematics, what we do is that we have to add a little bit constraint to the system that we're calculating. Okay, and the constraint here is that instead of having a plane wave propagating, in free space, what we'll do is that we'll put that plane wave in a pair of mirror. Okay, we let the plane wave, bouncing back and forth in between this pair of mirror. Right, so that when we do the integration, there's actually a finite limit, right? From not from minus infinity to plus infinity, but if this is z, then you have from 0 to L. Okay. And so the thing for this, for this lecture, okay, at least for today, is relatively simple, right? It's to write down the energy or the Hamiltonian of light in between a pair of mirrors, which sounds very trivial, and then it is in some way trivial, and then we'll show it to you guys here. Okay, so first let's define the coordinate. So z, x is pointing up, y is pointing out. Okay, x, y, z, like this. And then to further make our calculation simpler, we assume that the light is bouncing back and forth in the z direction. Okay, in the z direction, and then the x, well, and the electrical wave is pointing towards x direction. Right? Electrical wave is pointing towards x direction, and by using the Maxwell equation, you will see that the if you assume it's a transverse wave, then the magnetic wave is actually perpendicular to electrical wave, and it's also perpendicular to the direction of propagation, so that you can naturally tell that, okay, the magnetic wave must be on y direction. Okay, y direction. So just to make it fairly simple, we say that E, okay, is EX, E. Okay, B is EY, B. Right. Okay, so when you do this, all this product curl, you can kind of use a simple rule, okay, to figure out the number there. And the key, okay, is to see if light is bouncing back and forth in a resonator or in a pair of mirror, then what is the electrical wave and magnetic wave that's allowed inside here, okay? And then and once we solve E and B, then we can do this integral and figure out the Hamiltonian of the system. Now let's see how to break this down. We first solve the electrical wave, okay? And then when we solve the electrical wave, then you see that there's a relation in Maxwell equation between magnetic wave and the electrical wave. Okay, two of them, depending on which one you want to use. And you can actually, from here, you can get magnetic wave, and then ultimately we can solve the Hamiltonian. So for the electrical wave, okay, we can treat it relatively simple. Okay, we can assume that, okay, it's a beam, okay, with certain area, and then on the z direction, it's just have a e I k z, the wave function, the wave number, wave vector. So let's see the electrical wave, and on the electrical wave, and what we can say is that, okay, there are actually two of them, right? One is propagating forward, the other is reflected backward, right? So when you write this down, you have to write down, okay, there's a positive, we say forward, we use plus to represent it, and then there's a minus, right? Minus means backward, and both of them have their electrical wave pointing at the x direction. So you have Ex, okay, and then you can assume that let's say this. You can assume that their magnitude is the same. The mirror is perfect, right? Whatever going forward will be reflected backward. So you will have E, okay, T. Here we add 1/2 here, the idea is that, okay, you're splitting the power between forward and backward, but technically you can add any variable, you can add any number here. Okay, so and then you have minus I omega t. Okay, in quantum mechanics usually, because in quantum mechanics the real number, the wave function doesn't need to be a real number, because the thing that count is its eigenvalue or its or the right, this one, the amplitude square. Okay, give you the distribution, so that you don't have to carry both negative frequency and positive frequency. You can just keep one. Okay, and then let's say forward is ikz, right? Ikz, and then the backward is relatively simple, right? It's the same polarization, same amplitude, and then same frequency, but then you have a backward k, right? K represent your direction, so you have a backward, so you have minus sign here, and then of course there could be a phase difference between forward and backward propagation, right? Imagine that when you propagate to this side, and then it really haven't finished one oscillation, then the backward could have a phase mismatch with the forward one. So here we just, in general, we say there's I phi here, and then later we'll say, okay, this phi in some ways a free parameter, and then it can be used to help us to simplify our equation. And so we can put the common things in the front. Okay, like this. And then you have okay. Or the other way is put the half in here. Okay, and if you know exponential equation quite well, then you can see that if I phi is 0, then this is 1, then this become a cosine function, right? Cosine kz. If I phi is if phi is 90 degrees, then there's an I here, then this could possibly become a sine function. Okay, and so the phi is really a free parameter that you can, let me be consistent with the note here. I use this phi. Okay. It's really a free parameter that you can use, and also the plus minus sign here is also a free parameter. You can add whatever, you can add whatever phase, a global phase in the front, and it's all fine. So in this case, we choose a phi such that the this thing inside, okay, this thing inside goes to sine kz, okay, sine kz, and this one goes to ex et e to the minus I omega t sine kz. Okay, you can choose other phase. Okay, you can choose other phase, and it wouldn't really change your solution here, because later you will have to do integral, and you can see what will happen here if you do an integral of sine square, right? E square. Then what you get is an average of sine square, and that's just 1/2. Okay, that's just 1/2, and it doesn't really matter whether you have sine or cosine here. So this part is kind of really nice that you have a little bit of flexibility. Okay, and then to make this, the reason that well, we have to define something next, and it will look kind of awkward in the beginning, but then later I will explain why, and then you will see that okay, it will make a lot of sense. So the definition here is that, right, although you already have this, so what we will define is, okay, that you still have your polarization polarization, okay, pointing upward. And then you have your sine kz, which doesn't really matter because later it will disappear in your integration. And then the next thing we do is to break this two, okay, into something relatively interesting. Is that we break this into two variables. One is A. A kind of represent you can think of it as it represent an amplitude of something. And then Qt carries all the time-dependent terms, including this epsilon I minus I omega t. Put it all here. And A and Q, you can consider A as a free parameter here, because think about it, okay, if you can put A as twice as large as E, and what that would do is it will put Q as 1/2, right? So by breaking this into two variables, you give yourself a little bit of flexibility, and then later we'll see, okay, this Q will actually become a position operator. And then when you do a derivative, okay, differential on time of the position operator, it will give you a momentum operator, and then this entire thing, well connected to quantum mechanics. Okay, so here in the mathematical sense, the way to break this into two is just to give you a free variable, a free parameter that you can tune your system. Now let's do a quick calculation, okay, to see the H, let's say HE, meaning the energy for the electrical wave part, and then that's 1/2 epsilon, and then E square dV, right? E square dV, and this gives you epsilon. Okay, there's A, which is a coefficient. Qt doesn't really matter. Well, Qt matters, but it's not a function of position, right? Because you're integrating over the volume. And then you have sine square kz dz dx dy. Okay, and here, okay, these two are just, in terms of x, y, z, they're just constants. You can put it in the front. And when you integrate sine square kz dz, what you can think about it is, okay, the dimension of this is z, is distance. And the sine square, on average, sine of anything is 1/2, right? So what this will be is it will become 1/2 of the distance here. Okay, 1/2 of the distance here. But of course, you can do it, the normal way, just to do this integration. So this one will become 1/2 L. And dx dy is integration of dx dy give you an area, okay? The dimension, the area would be, you can think about it as the cross area of the beam itself, right? So here, what we get is actually okay, 1/2 epsilon A square Q square. Okay, we put a 4 here because the 1/2 come in the front. And then you have, we say S effective, that's the area of your light beam, times L, right? L is the distance here. And this one have a dimension of volume, right? Dimension of volume. It's like the volume that the light occupy, right? With its cross section, it's traveling, it occupied the entire cavity. That's the length of L. So that eventually this one will become 4 epsilon V effective A square Q square. Okay, Q square. So this is the part that I give you here, and then it looks relatively okay. It's not terrible. and then all these two variables are known, and this one is a free variable. That's fine, and then you just have to solve for q. Okay, so this is this one, and then we'll come back a little bit with a short break. Okay. Now let's move on to calculate the second part, the energy for the magnetic wave. And then the equation we're going to choose from is actually this one. So we're going to use, B equals to mu epsilon partial E, okay, partial T. And the fact is that you can use either one, and then they will give you the same result. Okay, and here this curl, okay, is there's a mathematical note in page 5 on our lecture note, and you can check the detail. But here, one thing I want to mention is that okay, when you're doing this curl, always remember that there's only one component that's non-zero. That's a y component. It's because we assume a transverse wave to simplify the calculation, and because of that, you can kind of reduce this to this two. Okay. Right, on the x direction is a derivative of z, and then on the z direction is a derivative of x. Okay, and then it has to equal to your electrical field, which is this, and then right, derivative of t. Right, derivative of t here, it's what you can see here. Let's see, E, okay, equals to 1/2 V effective A QT. Right, so derivative of t is actually derivative of q. Right, so what you will get is you will actually get there's a sign here. Okay. Okay, and I think there's no 1/2. Okay, there's no 1/2. No, my apology. Okay. Sine kz, and then A, and then qt. Okay. Yeah, the area, and then those are come from the integration. Okay, so you have this one, and then you can write that down here. Just copy the e here, and then you have a derivative, and derivative is on q. So this one equal to a, well, ex, okay, a sine kz q dot t. Q dot here means time derivative, and you can see that okay, first of all, this one doesn't really matter because there's no z components, so you see that partial b partial x goes to 0. So this kind of tells you that okay, we're still in approximately in a plane wave approximation. Otherwise, what this tells you is that distribution is relatively, distribution across the xy plane is still relatively, I'll say relatively flat. Okay, and then so here then the only thing that matters is the ex components, right? The components pointing to x direction, and here you will get partial b partial z equal to minus sign here, and then lots of So then what you can do is that you can do this integration, right, to solve the b, and then you can easily see that there's a b. Okay, the integration of minus sign gives you cosine, right? So mu naught epsilon naught a q t cosine kz, and if you think about it, when you do the z derivative on cosine kz, it will give you minus, but also give you a k, right? So to cancel that, you have divided by k. Okay, so this is your b. Okay, so once you get b, then you can magnetic field. Then you can do the integration for the b field here, which is this one. B squared dv, right? And then you kind of have the same idea, right, as how we integrate this, and we can, first cosine square would become 1/2, then there will be a 4 here. Okay, and then b square, there will be mu naught square epsilon square a square k square q naught square. Okay, and then it will be v, right? V effective, because it will be in the integration. There's there's a distance and there's a beam size. Okay, so let's see. This is solution here. So we have b equals to EY, that's its polarization, the direction of the wave, and then mu naught epsilon naught a k cosine kz q t q dot t, right? And then hb will become 1/4. That's always there. Okay, 1/4, and then mu naught. Okay, because mu and mu cancels 1. Epsilon, and then epsilon. Okay, k square. Here you can notice that mu naught epsilon naught give you 1 over speed of light square, and k can be defined as omega divided by c, so that these two will ultimately cancel each other. And then okay, but we can keep going here, and then we have a square, which is the same here, v effective, which is also the same here, and then q naught t square. Okay, so we now know the energy of electrical wave and the energy of magnetic wave. Okay, one is a bunch of coefficient times q square, another is a bunch of coefficient times q dot square, which is the time derivative of q square. And if that gives you any idea, okay, of what it is, imagine the energy of a harmonic oscillator, right, of mass m, and then there's a spring that has a constant of k, and what that is, the energy of that is right, is the potential energy 1/2 kx squared, okay, and then the kinetic energy, right, and what is the speed, right? The speed is just the time derivative of position. So you have x dot here. So now if you look at this too, okay, there's some extremely similarity here, is that the energy is composed of two parts. One part is represented by one variable. Here is x, the other is q, but in a mathematical sense they're the same. The other is the other part is okay. There's that variable's time, derivative of time. Okay, that's shows you here and there. Okay, and so from a mathematical standpoint, when you write down an energy in a form like this, you can't really tell if this is a harmonic oscillator or is this a EM wave. Okay, and you might wonder, okay, how is that possible? Why there's such a link? The idea is very simple, is that if you look at harmonic oscillator, then what happens is that when it's oscillating, the kinetic energy is transferring to, is transferring with the potential energy, right? And then the solution, okay, the solution for this is a cosine wave, right? Think about it, it's a sine or cosine wave. And the EM wave is kind of the same thing, right? You have energy from electrical field transferred to magnetic field and transfer back to electrical field through Maxwell equation. And then if you solve the light wave equation, propagating light wave, we solved that before, and the solution is also a cosine wave or sine wave. So here, okay, what the Hamiltonian or what the energy really tells you is that in terms of energy conservation, that these two are the same because there's one form of energy stored in one place, and then later it transferred to another form, and then this can keep on going and going and going. So from this standpoint, point of view, your electrical field here is in some way the position. Okay, Q is the position here, and your magnetic wave is your speed, or you can imagine it in a quantum mechanical sense. Okay, mx dot. So your magnetic wave is actually a momentum. Okay, so in the next section, what we will do is we'll use this free parameter a. Okay, we'll define what a is, and then make these two Hamiltonian exactly the same. Then the next time when you solve EM wave, quantized EM wave, you don't really have to go through all this again. You just say, okay, it's a harmonic oscillator. I look for harmonic oscillator solutions. Now let's see how we can define the variable of free parameter a, okay, to get our Hamiltonian to the same as the harmonic oscillator. Okay, so let's first write down the Hamiltonian here is quarter epsilon v effective, and then there's a square, which is the same. Okay, and then you have q square t q square t, and then the other side it's mu naught epsilon naught k square q dot t. Okay, so let's leave it here this way, and then let's write down the Hamiltonian on the energy for the harmonic oscillator, which is here, but let's convert it into let's convert it into a function that we are more familiar with. That would be use this. Let's see, because the reason is that harmonic oscillator. The reason is that in quantum mechanics, right, we rarely use speed, right? It's hard to define the speed when you have a wave function. When you have a wave, you can say that the propagation of the wave have a speed, but that speed is different from this one, right? So in quantum mechanics, what we usually do is that we don't define velocity, but we define momentum, right? So we define momentum mx, equals to p, right? Mx equal to p, and when and then you have x equals to p squared, p divided by m, right? Okay, so when you plug that back in here, then what you will get is 1/2 kx squared plus p squared divided by 2m, right? So this is kind of normal. And then the other thing that you can change is that k is usually something that people don't want in their equations, because one of the reasons is, it's relatively difficult to measure k. Okay, but there's another thing. Well, there's another parameter that's very easy to measure, is the harmonic oscillator frequency, right? And that frequency, let's say omega, is the harmonic oscillator frequency. Omega is actually k divided by m, right? K divided by m, and the way to interpret it, well, I guess you guys learned this in high school or in physics 1. But the way to interpret this is that, okay, if your spring is very rigid, right, then it can give you a lot of, if you push it, then it can give you a very fast, responsive force. Okay, so that the motion will be very quick, so the omega is high. And on the opposite side, okay, if your particle is very heavy, then if the spring gives you the same amount of force, then you tend to move slower, right? So that's why m is down here. So if you use that, then if you use that, right? If you use that, then k will become m omega squared, right? Right, so it can be either this one, or it can be 2m, or right. So right, either one represent your momentum. So here, okay, when you look at this, then it's very tempting, right? And to just think, okay, you can let this term here, right? Because this term gives you multiply q squared should be the counterpart of this term, the potential energy, right? So a natural thing to do is, okay, you can do is define for V effective a squared equals to half m omega squared, right? M omega squared. And so here, okay, there are some obvious questions here. First of all, is what is m, right? Like this is a EM wave, right? Where's the mass? And the fact is that the m doesn't matter at all. The reason is, okay, a is a free parameter, right? It's a free parameter that you can use it to adjust. You can adjust the a, and when you adjust the a, the q will adjust correspondingly. Okay, so when you make this definition, and you can think of omega here, omega is the harmonic oscillation frequency, and here the harmonic oscillation is actually the EM wave, right? So this is actually omega. You can let it to be the frequency of the light, right? The harmonic oscillator. So then the m, okay, if this is fixed by the light itself, then the m become the new free parameter, right? So you're mapping the free parameter of a to free parameter of m, right? So you still have some flexibility here, okay? And if we do that, then okay, we can see a, okay, equals to 2m divided by epsilon v effective square root, okay, times omega. Okay, just let me double check. Yes, and then a lot of time people write it this way. Okay, so when you make this definition, then your Hamiltonian naturally become the same. The first term become the same. Now the critical part here is that if you think about it, look at here, right? There's only one free parameter, that is A. Okay, so whether this comparison from the between the EM wave in the cavity and the harmonic oscillator, whether it works or not, solely depends on now this term. Okay, does it transform to p squared divided by 2m, or does it transfer to this? Okay, either one works. But if there's other parameter that you cannot cancel, you cannot get an m here, that it means that there's something different, okay, between the EM wave and the harmonic oscillator. And you know, the thing I can tell you is that, okay, for an oscillator, right? For an oscillator, harmonic oscillator or EM wave, okay, there are different type of oscillators. You know, the way to think about it is that the parameter here, what it really means is that when your energy, okay, can you completely transfer the energy from electrical field to magnetic field, right? Is there a position where when your electrical field is minimum and then your magnetic field is maximum, right? If you have that, and it's similar to what you have here, is that you can transfer the energy completely from kinetic energy to from potential energy to kinetic energy, right? When it's back to the balance point, then it has a maximum speed. If you have that, then they should match. They simply should match, right? Because that capture the nature of their energy transform. Okay, so let's try that. So if we plug that in, so H, okay, the first term become m omega square q square t. And then the second term, okay, let's see, is m omega square. Okay, it's good to have m. And then you have mu naught epsilon naught k square and q dot square t. Okay, q dot square t. So here, then, you know, what we can do is that we can see mu naught epsilon naught equal to 1 over c square, right? That's a constant. We know that. And then k here, okay, notice that when we use this equation to calculate the energy, we are assuming we're in vacuum, right? We are assuming we're in vacuum. Otherwise, if you put the refraction index back, then this should change accordingly. So if it's in vacuum, then k is omega divided by c, right? K is omega divided by c. If it's not in vacuum, then you have n here, then you adjust the term here, then you can still cancel out, but you know, we have to be consistent. If we use the equation for vacuum, we have to keep the k in vacuum. Then this term, mu naught epsilon naught k square equals to 1 over c square times k is omega square c square, right? So you cancel that out. This term is 1 over omega square, right? 1 over omega square. Then, you know, this entire thing make a lot of sense now. Right, so you know, this is exactly like the Hamiltonian of a harmonic oscillator, and then you can define MQ is PQ, PT, MQ dot T. So define momentum, you know, which really doesn't matter, right? So, and then what you will have is you have m omega square q square plus p square divided by 2m. Okay, p square divided by 2m. And of course, if we do that, then you know, you have to remember your definition. So when you plug back to magnetic field, you know you know that there's a factor of m here. But the reason that we can do this in a kind of casual way is because we don't really care about the magnetic field. We always calculate the electrical field. So this is perfectly fine. Okay. So now what I'm going to do, okay, is I'm going to make an argument that you either accept it or you give up quantum mechanics. Okay. So the argument here is that from a mathematical point of view, okay, if you believe that quantum mechanics is governed completely by the Hamiltonian, right? You have a Schrodinger equation, and Hamiltonian is the only thing that matters here. If you believe that the entire system evolution can be determined by the energy form, okay. First of all, if you don't believe that, that's fine. You can still go to analytical mechanics, and then there's actually two theorems. One is Lagrangian, the other is Hamiltonian. That you can see that from the energy, okay, of a system, you can derive Newton's law, F equals ma. So in classical mechanics, actually knowing the energy is equivalent to knowing the force or knowing the and then knowing the motion of the system. So if we use that argument, okay, if you believe that knowing the energy of the system, then you know the evolution of the entire system, okay, evolution of the state of the system. Then based on that, okay, the Hamiltonian, because the Hamiltonian of a harmonic oscillator is exactly the same as the Hamiltonian of the EM wave. So there should be no difference. There should be no difference at the solution, okay, between these two systems. Whatever you solve for harmonic oscillator mathematically is the same as what you solve for the EM wave. And of course, you can say, okay, the interpretation of that is different because here x means position, q means momentum, and here x means position, p means momentum, and here q means electrical field, p means magnetic field. Okay, and that's the difference. That's the only difference. Okay, so if you accept that, if you accept the mathematical form governs the evolution, then the next argument we can make is that in quantum mechanics, we make p goes to 1 over IH bar partial x, right? Say p, we let the momentum goes to an operator right? We let the momentum go to an operator so that when it acts on a plane wave, it gives you h bar k. That's the momentum of a that's the momentum of a particle, momentum of a photon. And then when you have this, then your Schrodinger equation suddenly becomes a differential equation, and then you can solve the energy. Okay, so if we accept the fact that the harmonic oscillator and the EM wave have the same mathematical form in terms of their Hamiltonian, then what you can do here is for EM wave, right? For EM wave here, the P is the same as here. So P goes to an operator, okay, which equals to IH bar partial Q, right? Because Q is the equivalent to X in the Hamiltonian. Okay, if you do that, then let's see, we can write it down now. EM wave, H of the EM wave is m omega square Q square plus P square 2m, and P is So this is actually called quantization. Okay, this is actually called quantization, that you change from an energy which is, well, which is in classical physics is a variable, it's a number, to an operator. Okay, this is called quantization, and it's made in a mathematical argument. Okay, mathematical argument that because you can do this for x and p for position and momentum, and because mathematically, okay, this is a generalized position and momentum, so you can do that to this as well because mathematically they are the same. Okay, and once we have this, okay, then we can use the complete, everything in Schrödinger equation and then in quantum mechanics, and then to calculate the evolution, or to show you, okay, what is really a photon. So before we end, I want to quickly summarize, okay, a few points here, because like we move from Maxwell equation to Schrödinger equation, which is a huge jump. Okay, so what is Q and P? Let me go back here. Q is electrical wave. Okay, we can think about it as a component in the electrical wave. P, you can think about it for momentum, but what it really is a component in the magnetic field. Okay, in the magnetic field, and the Hamiltonian is the energy of the EM wave. Okay, and you might think, okay, now what is psi? Okay, what is psi? Right. Okay, what is psi? And this is actually a really good question. So let's ask ourselves the question. Okay, if you have psi in quantum mechanics, if you have psi and then x, okay, if you take amplitude square of that, what does that mean in quantum mechanics? In quantum mechanics, okay, if you open any quantum mechanics textbook, what it means is that the probability density of finding the electron or the particle you're solving at position x. At position x. Okay. So now if you change x into q, okay, if you change x into q in your EM wave, what that means is that the probability of finding your electrical wave at the magnitude of q is this. The probability density of finding the probability of density of finding the electrical wave at the magnitude of q equals to your wave function amplitude square. Right? So this tells you the probability distribution of your magnitude. Okay, of your magnitude. So just imagine that for a moment, and then we will stop here today. Okay, and then next week, okay, next class, what we will do is we will use this harmonic oscillator, or this Hamiltonian, and then we'll use something called second quantization, and then to show you that the simple solution for the photon is just h bar omega, and then we'll start from there, and then move towards how to use quantum mechanics for nonlinear optics for light and matter interaction. Okay, that is all for today. Thank you.